Okay, let us begin our today's seminar, and it's a great honor for me to introduce you our good colleague, our former graduate from Moscow State University, Iliya Tolstikhin, who is now postdoc in Tübingen, right? Still postdoc, right? Working with a group by Bernard Sharkov, who will give us a presentation about the recent results on some theoretic justifications of generative adversarial networks, and in particular, an application of boosting-like procedures to GAN.
Yes. So thank you for introducing me, and thank you for inviting me here. I'm very excited about this talk. Indeed, I am still a postdoc in the Max Planck Institute for Intelligent Systems, which is in Tübingen, Germany, and I work in the group of Bernard Sharkov. And I will be talking about this work called AdaGAN Boosting Generative Models, which is actually accepted for this year's NIPS after being rejected for this year's ICML. And as it usually happens, actually, we almost made no corrections to the second submission. It had great reviews on NIPS, so finally got it. So in today's talk, I will be discussing this recently introduced, well, they were introduced a couple of years ago, the generative adversarial networks, which are nowadays hyping, I think, many. So who did hear about generative adversarial networks? Right. So every conference, every top conference receives hundreds of submissions on this topic. And this is a field of unsupervised generative modeling. So just to roughly describe the idea of a problem, you observe a bunch of data points, let's say pictures, and you want to train a machine, or you want to train the model which will spit out random points which hopefully should look something like the training points. So this is a very loose formulation of our problem. And originally, the very first paper by Jan Goodfellow and his colleagues was called Generative Adversarial Nets. And it attracted community because basically they reported synthetically generated MNIST digits, which looked very good, very nicely. So they had very sharp edges, and these pictures looked very cool. Especially, so basically there were several methods already solving these tasks, one of them being variational autoencoders. But somehow variational autoencoders was producing blurry looking images. And compared to variational autoencoders, the pictures reported in this first paper, which was, I think, 2014, they looked very sharp. And people somehow lost their mind and started altogether exploring this field of adversarial training. So today's talk will be exactly about these algorithms. And here are some of the, nowadays popular pictures. So basically all pictures here are generated by these trained networks. So they are not real. These are deep nets trained on the training data, and they are capable of producing quite realistically looking human faces. I don't want to get in details about all this, geometric structure in the latent representation. I will mention it later. But basically, these pictures look kind of cool. These are generative adversarial networks trained on. Can you guess on what?
Album covers.
Exactly, on album covers, exactly, and they kind of look cool. So nowadays they're also capable of producing very, I would say, quite realistically looking images, including those, birds with very thin legs, and at least all the, anatomical structure properly captured. And then, nowadays people go crazy training GANs on all type of data sets. So do you know which data set was used for this? Pokemons, yes. So this was a Japanese guy who trained GANs on Pokemon. So basically this field is now very popular. And yeah, so it's very interesting field. Many people are attracted to this field, and many people from machine learning working, having variety of backgrounds, they start working on this topic. Dozens of papers being submitted, so I think I counted, and at 2017 ICLR, if you just opened the web page with submissions and you search for generative adversarial something, there were 15 papers just matching this title, and most of them got accepted actually. And then, as perhaps some of you know, in NIPS 2016 in Barcelona, there was a huge tutorial on GANs by Jan Goodfellow, 2-hour tutorial. And this was, I think, the largest of all tutorials. Okay, second largest, because there was also a tutorial on, I think, deep reinforcement learning happening in parallel. And then the GAN workshop was actually second largest at that NIPS. So clearly this field is, very popular, lots of people working there. So now, just to motivate, so just to tell you, a bit of a background, how did this sorry, I didn't say, but this project is together with Bernard Scholkap, with one of his PhD students, Carl Johann Simon Gabriel, and with people from Google Brain, with Sylvain Iliya and Olivier Bousquet. So now, our motivation was, so we are people with mostly theoretical background, and before that, personally, I was writing only theoretical papers where I was proving certain inequalities. And this talk will actually not be different. I will be showing you inequalities. But our motivation was that, people were trying to improve those generative adversarial nets because there are certain drawbacks of these methods. And hundreds of papers were proposing certain, heuristics, some ad hoc ideas to actually improve the GANs. In some cases they worked, in some they did not. But the thing is, this more or less looks like, a brute force search. So right now the field is in its state when people are, performing brute force search through all the reasonable ideas to try them out and to see if some of them works or not. And this is basically quite natural. It's an okay situation, especially considering the fact that field is young. But now it almost feels like there are too many papers which already tried something, and many of them reported very nice empirical results. And perhaps it's about the time to try to understand what is actually happening, why some of the methods are working nicely, while others are not working as good as expected. And this was basically our motivation, to dive into all this GAN community, and to try to explain and understand at least some parts of this story from the theoretical point of view. And this talk will be about some of the theoretical aspects in the GAN community. By the way, I think, so I will be okay with you interrupting me asking questions whenever you have them. So just feel free to raise your hand and ask. So okay, so the thing with GANs is, okay, they're producing quite nicely looking pictures, but those of you who tried training them is a mess. It's quite hard to make them generate nice pictures. It's certainly possible, but it requires certain amount of time, hyperparameter tuning, some dirty hacks. So you will not learn about all these things from me today. I am not going to tell you how to do this. So what you will learn today is I will try to give you at least some of the recent ways to explain what GANs are actually doing, and a theoretical explanation for that. And then based on it, I will tell you about this algorithm which we developed called AdaGAN. So one of the problems of GANs is the so-called mode collapse. So if you train GANs on certain set of pictures, often you will notice that they start producing quite nicely looking images, but they will start producing, only a small subset of those which you had in the training set. This is a very typical situation, and it's called mode collapse. And basically, back then when we started looking into this field, people were discussing exactly this problem, and back then it seemed that this is one of the big problems in the GAN field, and we were very optimistic and passionate, and we decided, okay, let's try to solve at least this problem. And this led us to this algorithm called AdaGAN. But before basically diving, okay. So this algorithm AdaGAN. So before starting any formal discussions, let me just, give you a very, very intuitive explanation of what the algorithm does. Okay. So if we agree on the fact that GANs are capable of producing realistically looking images, so let's agree on that fact. This is something more or less, believable. Okay, there are this problem of mode collapses, but at least those pictures which are generated, they look nice. If we agree on that, here is the situation. Imagine you have a huge corpus of pictures of all types of animals in the universe. All the animals. Now imagine you run your GAN, your favorite black box GAN implementation, and it starts producing awesomely looking cats and dogs. Okay, good, but you want giraffes. Why giraffes are not produced by your model? This is exactly what can happen if you observe this mode column situation. So GAN is producing only cats and dogs and ignores all the other animals. So now, how could you make it produce giraffes? So idea is the following. If you see that your trained model, let's call it the first model, okay? So you trained it, you froze it. It is producing cats and dogs. What you could do is you could manually take the whole data set and replace all the pictures of cats and dogs altogether and run another independent instance of GAN on the remaining dataset. Okay? So now, if we agreed on the fact that GAN is capable of producing something reasonably looking, it will start producing something reasonably looking, and this time it won't be cats or dogs, because it never sees cats and dogs in the modified dataset. So perhaps it will start producing crocodiles, I don't know, and kangaroos. You can proceed in the same manner, iteratively, every time manually replacing pictures of the last generated model, and perhaps eventually you will get the model also generating giraffes. And if you keep going on, perhaps you will cover all the existing modes in your dataset. Here, I mean, so okay, we still need to define what is a mode. In this case, I'm using this intuitive assumption, yeah.
Yeah, basically I have a question related to the explanation of AdaGAN.
Right.
So basically, one of the nice properties of GANs that people usually like a lot is that you can interpolate in the latent space and then you get reasonably looking images.
Yep.
So when you have multiple generators,
right,
will you be able to interpolate across them?
That's a good question. That's one of the downsides of the model, because you lose the manifold structure of the AdaGAN, but I'll turn to this later, and that's a nice question. So for now, let's say that we are only worried in generating realistically looking images. Actually, this is a big question. Why are people training GANs? And to me, it's still not completely clear, because all GANs allow you to do is to sample images. So I often ask my colleagues, okay, imagine we solve the problem. Imagine there is a super stable, cool algorithm which trains, very stably, quickly, and imagine you start sampling realistically looking images from your data set. So I still have a problem understanding what is it that people will do next with this existing solution, but for now let's assume that this is all we want to do. This is actually all, large part of machine learning field is right now concentrated on exactly this problem, so let's try to solve this problem. So does it make sense, this algorithm which I told you? This iterative algorithm. So in the end, of course, when we run all the iterations, what will be our model? We will just uniformly weight all these components. So every time, imagine you ended up with 1,000 trained GANs. You will flip a coin with 1,000 edges. You will choose one of this model, and then you will sample from it. Okay?
Oh, it depends on the number of components.
Yeah,
of course.
It seems the huge number.
Okay, fair enough. Good question. Any other problems with the algorithm?
Are we sure they are weighted equally?
That's also a nice question, and I will address it later. Perhaps we indeed don't want to weight them equally, because maybe there are animals like, I don't know, pigeons, and perhaps we see a lot of pigeons, and there are very few pictures of some other animal. In this case, of course, we don't want to produce pigeon and, I don't know, some rare species with exactly the same probability. So yes, this coin flip should not be uniform. That's a nice point. But is there any other problem with the explained algorithm?
Constant retraining requires a lot of time.
Okay, still having lots of...
We need to have labeled data sets.
Why?
In order to identify those modes.
Exactly. Okay.
Or you just need a way to throw away examples.
Exactly. So I wanted to hear that, but that's actually, so perhaps your comment is more about when do we actually start? When do we say that, okay, we are now generating all modes? But this is also related to the question which Anton raised, which is, on every step we need to be able to throw away from the data set those things which we believe are already generated, right? And I said we will do this manually. But of course we don't want to do that manually, it's impossible to do, right? So the rough explanation of idea is the following. Imagine you are generating cats and dogs already. So your model, the very first model, is already generating cats and dogs. What you could do is, you could take your training set, you could generate bunch of cats and dogs, bunch of fake, so I will call fake whatever is generated by the model. You could take your training set, you could generate bunch of fake dogs and cats which are generated by your current model, and you could try to run a classifier which will try to separate between those two sets. Okay?
Between the real dogs and cats and fake?
Exactly.
Mm-hmm.
So the training set still contains everything. The fake set is something which is being generated by our current model. So intuition is that if the model is doing good job in generating cats and dogs, classifier should perhaps have hard time telling between cats and dogs from the real data set and from the fake data set. But when the classifier is shown the giraffe, it should easily say that giraffe is a real image, because giraffe never appears in the fake data set generated by the model. In other words, what I want to say is perhaps you could train a classifier and then look at predictions of the classifier on the training set to understand which of the examples are already covered by your current model and which are still undercovered. So so covered examples will be those on which the classifier is making an uncertain prediction, saying that, I'm not too certain that this point is from the real data. So basically, classifier is solving two-class classification problem, on real and fake, right? If classifier is with high certainty answers real on some point, it means that this point is not surrounded by the fake points. So this may be the giraffe, which was never generated by the fake model, right? So those points are undercovered. Those points are exactly the points we actually want to generate in the future. And if classifier is saying for a point from the training set, oh, I am 50% certain that that's a real point, it means that this is the point which is surrounded by the fake points from the second class. Okay? So the main idea of the AdaGAN, which stands for Adaptive GAN, is after training, on every step it trains GAN, okay? But it does so with a reweighted training set, where the weights are computed exactly in the way which I told you. Those samples which are easily classified as real are upweighted, and those which look kind of similar to what is already generated are downweighted. And when we run GAN, for those of you who already know, we are using something like stochastic gradient descent with mini-batch, and we are sampling actually from our training set. So usually you would sample from a uniform distribution over your training set to get a mini-batch. And here you will sample from this you will be performing importance sample with those weights which you tune every step after training the current GAN model. So every step, so here is a pseudocode. At first step you have a uniform distribution over your training points, and you train vanilla GAN, whatever, I don't know, black box implementation of GAN, your favorite one, with these uniform weights. You get the first model, okay? Now on each step, what I didn't say and what was asked before, of course we don't want to uniformly weight all these trained GANs, and perhaps we want to weight them with different coefficients, right? So these coefficients are called betas. So beta t is the coefficient I'm going to assign to the model trained on tth step, okay? So this says, choose coefficient for the next model, update the training weights, which means instead of uniform, now you need to update them according to the procedure, something like procedure I described you with the classifier. So reweight the training set and run GAN on the reweighted training set. So let's say if you are generating perfectly looking cats and dogs, you're hoping that weights corresponding to the true cats and dogs in the training dataset, that they will be very small. And what does it mean? It means that this model will very rarely sample them, meaning it will very rarely see them, which kind of makes us hope, at least, that perhaps it won't anymore generate cats and dogs. But it will instead concentrate on certain other part of the space which is still undercovered. Okay, so this is kind of a bird's eye view, very rough explanation. Yes?
When you invented this, do you really think about cats and dogs or about boosting and possible inequality that you already have?
We started with exactly cats and dogs, and then it turned that after we derived all the equations, that it looked very similar to what's happening with AdaBoost, which I will mention a bit later.
Because this scheme is just another boost.
No, that's not true, because AdaBoost is about very particular surrogate laws for binary classification. You introduce this exponential upper bound, and then it has all these nice properties. So, and then, okay, I wanted to turn to this later, but basically the strength of AdaBoost is, of course, first that this algorithm has a very nice, so empirical risk minimization with these exponential laws can be made in a very closed form, very elegant theoretical way. But the main strength of AdaBoost is about theoretical guarantees which can be provided. This theorem saying that, you know, if for any reweighting of your training distribution you can achieve, so about this weak learnability, if you can achieve at least, you know, 0.5 plus epsilon accuracy, then the overall average classifier will be strong. So this part of analysis will also appear here. But there, the criterion was 0-1 loss on the like we were worrying about binary classification, right? Here, we are discussing similarity between distributions. There is a data distribution which is generating our training set, and we are fitting another distribution which we hope to look similar, right? So we have a different measure of quality of the model, which is f-divergence, which is basically something I will be talking about during next slides. Yes?
So I have a question about how you choose the mixture weights, because in AdaBoost the mixture weight depends on the quality of the classifier.
Of course.
And here you choose it before even training GAN. So how is that?
That's a nice question, and I will show you all the answers. So that's an outline, actually. This part was introduction to motivate. So now you already know about this algorithm. Basically, I'm not going to tell you anything new. I will just show you how to compute. So basically, this idea with classifier, right, which I told you. You train a classifier, then you choose your weights according to how certain classifier is on this point. Yes?
I will have multiple classifiers.
On every step, you train new classifier. So every step, you have certain pre-trained part of the model. Let's say you already trained 10 GANs. On 11th step, you would first start with training a classifier, trying to separate the whole training set from the fake training set sampled from this whole model consisting of 10 components. Okay? So every time you're trying to focus on exactly this part of the training set which is missing. Yes, so this is costly every time you train a classifier, and of course next step depends on all the previous, so you cannot make it parallel, it's hard. Yes, there are many downsides, but also there are positive sides which I will...
But like to defend this, like training a classifier is probably way cheaper than training a GAN.
Of course, yeah.
But GAN is the
Exactly.
problem.
Exactly. Yeah. So the talk will be basically roughly 3 parts. First, I will motivate this idea that GANs are very much related to something known as f-divergences. So my claim would be here that we could look at GANs as methods to minimize the f-divergence, which is basically a measure of similarity between two probability distributions. So here, imagine P data is your unknown data distribution. You only have a sample from it. You don't know anything about it. And here is your model which you're trying to tune. So GANs allow us to minimize the f-divergence between these two things, where f-divergence is a certain measure of similarity between probability distributions, which I will tell you about. Okay? Once we agree on that, the second part will be somehow abstract, and we will, for the second part, forget about GANs. I will tell you about the following problem. Imagine you want to solve the following problem. You have certain probability distribution, okay? And you want to construct a mixture of distributions so as to minimize f-divergence between the mixture and this model, or this fixed kind of reference distribution, okay? And imagine you want to do it in a greedy fashion, meaning on every step you want to add a new component to your model, but your final goal is still to make this f-divergence as small as possible, okay? So this is an abstract theoretical question regarding approximating distribution with mixture models in f-divergence. Okay. And I will show you certain theoretical results we derived on this problem, which basically shows how to make these iterative updates in such a way which will lead to geometric improvement in terms of this f-divergence.
Geometric improvement, what does it mean?
I mean the quality of your fit on the next step will be some beta times quality on the previous step, where beta is smaller than 1. So you will be converging exponentially fast to 0.
But beta depends on the step.
Beta depends on what?
On the step number.
Beta we can choose, I will show you. Beta basically you can choose whatever you like.
0?
Not
Choosing
so-
beta 0 will be the best. I will talk about it, it's actually a funny question, but we will see that. Okay, I still need to tell you what this beta is, what this beta 0 means. Basically, theoretically, we will see that indeed setting beta to 0 will be best possible option, but in this case we need to believe that GAN will exactly match the current distribution, which never happens.
Is f-divergence a symmetric function?
No, we consider any of divergence you want, all of them.
And so why have you chosen
This direction.
This direction.
The thing is, for any of divergence, there is a modification of f you can perform such that you flip the coordinates. So it doesn't matter basically in which order to spell it. So the results will be general for many.
You mean for any f that exists f prime?
Yes, such that it flips the order. Exactly. And finally, after completing this, I will turn back hopefully to GANs and show you basically this AdaGAN procedure, which will be these theoretical results specified to GAN algorithm. So I'll try to quickly go through this boring slide. So basically, this monster is called f-divergence. You take two distributions defined over the same input domain. All you need to do is to choose this function f, which should be convex. It should be a mapping from positive line to the real values, and it should satisfy hopefully this structural condition, taking value 0 at point 1. Then you can spell out this integral. So I don't want to dive into details because it's still a question. So basically this is a ratio of densities, but to define density of distribution you need to specify with respect to which measure you're defining these densities. So I want to kind of forget about all these structural probabilistic assumptions about sigma fields and all this stuff. So let's keep it a bit high level for now. So imagine this is just a ratio of densities of these two distributions. You can think about cases when the densities are nicely defined, like everything, full support, like Gaussians, then you have your densities. And we are integrating over this second distribution P, okay? So now, there are certain nice properties about this expression. First of all, you can, because f is convex, you can use Jensen's inequality to show that it is non-negative. If you assume something stronger about function f, basically you need to say something like it's strictly convex. Then you can show that it equals 0 if and only if p coincides with q, which actually makes us believe that perhaps this is a nice way to define divergence between distributions. Okay? You have something non-negative, it takes value 0 if and only if two things coincide. Unfortunately, there are many bad things about it. For instance, it's not symmetric. And if you want to use this as a measure of distance, it would be, it won't hurt if it were symmetric, right? But it is unfortunately not symmetric. And moreover, it does not satisfy triangle inequality, so this is not a metric, okay? But you can still use it as a divergence measure.
What about invariance to nonlinear transformations?
Yeah, it's written here, so I wanted to skip this, but basically, for every fixed f, you can perform certain transformations to f by still keeping the same of divergence. Basically, you can, I think, perform affine transformations to f, and you will end up with the same f divergence.
Mm-hmm.
So this exactly means that it's invariant under, I think, affine transforms.
And what about non-affine?
Then I think you don't have general
Because
results.
KL is invariant.
Perhaps for KL divergence you have some special statement, right? So other things which I wanted to mention is So there is at least one metric in this class, which is total variation. So total variation is this, basically you're integrating absolute value of difference between densities. This is a metric, it satisfies triangle and all the rest. There are also other famous elements here, Kale divergence, Hellinger, as I said, total variation, and some others. And Jensen-Shannon entropy, which is another thing which will be important for GANs. I will mention it later. Yeah, here so basically here I'm just specifying which function f corresponds to which divergence, and this is this beast Jensen-Shannon. We will get back to it later. So here are just examples of two of the elements of this f-divergence class. So as I said, because we want to minimize f-divergence between two distributions, we kind of want to know what does it mean for two distributions to have small f-divergence. And this slide just shows that depending on f, you get different behavior. So if you take Kale divergence in this way, meaning you are minimizing p to be close to q, right? You can show that this corresponds exactly to maximizing marginal log likelihood of p under q. Okay, and this have this nice Bayesian interpretation. And this is basically a classical divergence considered in many of the works on statistics. And this guy have very nice justifications. And you can end up also with this also corresponds to maximum likelihood estimation. In the other direction, so if you just flip those, Kale divergence is not symmetric, so you're getting something different. And it actually behaves in another way, in a rather mode-seeking way, basically. If you will try to fit mixture of two Gaussians with one Gaussian using this guy, you will end up with this one Gaussian trying to concentrate around one of the two blocks. So this is a different type of behavior for this model, because if you try to do the same in this order, this one Gaussian will try to cover both Gaussians by simultaneously so first and second moments of this one Gaussian will fit exactly the first and second moments of the mixture. So these are two different behaviors. And if you choose yet another f function, you may end up with something else. So this is just to say that these guys are all different. So now regarding GANs. So here I will present certain general way of introducing GANs, not exactly the same way as Goodfellow did in his original paper. And then I will show that actually the way he did in the original paper is just a very particular instance of this general family of algorithms. So here I perhaps will write something down. So this is a whiteboard marker, yes. So now this is an f-divergence, and there is this neat trick called variational representation of f-divergence, which says that f-divergence, which is this integral, can be written equivalently in a slightly different way as a result of optimization problem, where this sup is taken, so forget about this domain of f star, this doesn't matter right now. Think of this supremum as supremum over all the functions defined on your input space, mapping to the real line. Okay? And then you're trying to maximize difference between these two expected values. One comes from distribution Q, another from distribution P, and what is interesting here, you have this f star function, which is a convex conjugate for f. So how many of you knows what convex conjugate is? Okay, so for those who didn't raise hands, here is a definition. Okay, so for any convex function f, you can define this guy called convex conjugate f star of x in this way. Here supremum is over real valued u. Okay, and so this is a definition for for function taking the real argument. Okay. Basically, the idea roughly is if you have a convex function, at every point you can draw a tangent. Okay. And the thing is then the original convex function, equivalently, you can describe it using set of all these tangent lines. Okay? And exactly the same thing may be applied to any other convex function. I use parabola, but as soon as function is convex, you can do the same trick. And there is one-to-one correspondence between these two ways. Every convex function you can explain either directly or through these tangent lines. Okay? Now, so this looks quite cool, right? And it looks quite mysterious. Okay, how come this happens? It's a bit weird because here we had some integral, you know, and here we have some optimization problem. So I cannot resist the temptation to prove it because it's a one-liner, and when we know the proof, we better understand the result, and we are not afraid of it anymore. And this result is important in my talk, and I don't want to certainly you to be afraid of it. So, first of all, I can write exactly the same expression by flipping f with f star. The thing is, f star defined in this way, you can show that it is also convex. So you can again apply the definition of convex conjugate, this time for f star, and in most reasonable cases you will end up exactly with f. So convex conjugate of f star is f. So writing this, I will get f of x if, so let me first write. Here, what I'm saying is, if f of star is a convex conjugate of f defined in this way, if I perform this conjugation once again, I will end up with f. Okay, so I mean, this is the same result. Basically, we just applied in other direction. Okay. So now, if we start from definition of the f divergence, so f divergence between q and p, so is integral over the input domain f of dq dp in x dp of x. Okay. So now what I'm going to do, so this is a value of this function at this point, right? So this is a number, this is a real valued number, right? So I'm going to take this identity and just insert it here. Okay? What I'm ending up with is supremum over real valued u, so this is a real valued u. So now I need to put x, right, the argument. What is my argument? My argument is this guy, this ratio. dq over dp of x, right? Now I need to put this u times u minus f star of u, right? But we were integrating with respect to dp, so this all comes in square brackets. dp of x dx. So no magic, so far so good, right? So what happens now is this dp enters the square brackets, cancels this term, and here, let me perform this.
Excuse me, what does it mean? dp dx?
Yes, this is a bit.
Okay, sure. Yeah, sorry. Yeah.
So
I could write either p small of x dx, or, but I am actually considering the Lebesgue integral here, so I will keep dp of x if you're fine with it. Okay. Yeah, this notation, I agree. I mean, okay. Let's
Well, actually, further in slides, you'll see dp as a measured Radon-Nikodym divergence according to the best measure.
Sure. So let me write it this way. Okay. So we happy with this?
Yes.
P small is a P small is
chance
a,
for a big measure.
okay, sorry for confusing you with this. I am also confused already. So let's make it. So Q of x over P of x. Okay. So these are densities. Let's say they are properly defined. Okay. So now, so first of all, we take this guy inside. It cancels here. So what we have is supremum q of x times u minus f star of u p of x dx. Okay. So now the cool trick. Look, for every x, we are solving independent optimization problem with respect to u, right? So u star maximizing this expression, of course, depends on x, right? Because there are certain things depending on x here, right? So now, because we are doing this separately for every x, we could as well say that let's take supremum over the function u of x, and we will have q of x, u of x. So let me first write. So what I did is, for every x we have u star, right? Which maximizes this expression. Meaning there is a function u star, and when you apply this function to particular x, you end up with this exact u star at this x point. So instead of solving independent optimization problems for every x, we could as well say that, well, we are just searching for a function which simultaneously minimizes all of them. Okay? This function may look nasty perhaps, but it's a function. It takes x and returns you some u star. Okay? So and now if you stare here and there, so now this g is exactly this u. Here you have, so q of x dx is expected value with respect to q of g of x, which is u of x. And then you have this guy, p of x dx integrated, which is exactly expected value with respect to p of f star u of x, g of x. Yes?
Excuse me, why do you have an inequality? Why is it equality and not inequality?
Yes, so you want to say that it's an upper bound?
Well, for me it looks like it should be less than equal to.
Can you explain why?
Well, you said that we have a
Max
particular function, star of x, and in the last expression we take all the functions.
Right, sure, but I said, so I didn't specify any structural properties of this function, so I said basically choose whatever mapping you like, but this, if for fixed x you choose this u star, you will exactly maximize this whole guy altogether.
Well, I don't.
So let's take this offline and I can discuss with you this. So my claim is, okay, you may be right, but my claim is in many reasonable cases you get equation, and those cases when you don't get equation are particular cases when actually you have a these cases may happen with probability 0, basically, this is what I'm going to say. And probability 0 we don't care because we are integrating out with respect to the measures.
Okay.
Okay, so now that we are familiar with this guy,
I have a question.
yep.
This whole thing, the whole statement looks a lot like the MMD, the mean maximum discrepancy, except by the difference is in the f star. Would it correspond to any meaningful f divergence if f star is an identity function?
If f star is an identity function, f star, not f,
Yes.
but f star.
Right.
So what's a conjugate of f star, of an identity function?
Well, identity function is still
It's still convex,
Yes,
yeah.
yes. I'm just trying to see what is
Isn't
it.
it Dirac? Because they're like.
But Dirac is not convex,
Right.
so it shouldn't be. Delta function?
Okay.
I think you get data, right.
Inverse Dirac.
So basically that's a very reasonable and nice question. So
Delta is not convex.
So basically.
We should come
Well,
to
still
some
not
convex function.
It's still not convex.
No. It will be like the function that is like.
you know, it is 0 here and everywhere else it's constant. Yeah,
But
it's
this
kind
is,
of
this
an
is not convex function.
It is.
no, it is. So
It is.
so
It
once
is.
again, you have like.
It is generalized
Yeah, it
convex
is
function.
okay. So basically, this is a very deep question. I have an answer for that. It's a bit unrelated to this talk. So there are GANs which are doing MMD. You can minimize certainly MMD with exactly the same trick I'm going to discuss now. But there in MMD, you actually don't need to perform the trick of numerically solving this because for MMD, you know analytical solution. We can talk offline again. So now basically, once we know this, there is a very cool trick. So basically now if you want to minimize this guy, let's say with respect to Q or P, whatever, you can instead try to minimize this So let's say you are minimizing with respect to the second coordinate, p. Okay, then you want to minimize this guy with respect to p. Okay, so inf over p of this guy is the same as inf of this sup. I just rewrote it. It's here. So now the idea of GAN, which is called this general f-GAN, which was a paper by Sebastian Novozin, published after the original paper by Young Goodfellow, it tells you the following. So this is a supremum over all possible functions. Do we have some nice flexible class of functions which we believe is powerful enough? Deep nets. Let's try to solve this numerically using deep nets. Okay? We kind of believe that they are flexible, and we know that for some reason we are capable of optimizing through this function class. So let's parameterize this g function with deep nets. Second, so we need to commit to certain model p, because p is something we want to tune. We want this distribution to have certain parameters so that we can tune it actually. So let's say p is the following distribution. You first sample, you choose certain latent space. For this talk, you can think of it as a 50-dimensional Euclidean space. You call it latent space. You define your favorite prior distribution over the latent space. Let's say standard Gaussian in the 50-dimensional Euclidean space. You sample this z guy from pz, which you call the latent code, and then you take your deep net, which I call here g theta. So theta are parameters of this deep net, and deep net is a function. If you fix parameters, you get certain function, right? So, and you will pass this noise through this function. So because z is random, this guy is random, and it has certain distribution. And it lives in the input space. This will be the function taking a latent code and spitting you out an image. Okay? So we just defined the type of models we are going to use. These are usually called implicit generative models. Why implicit? Because if you write down the analytical form of density of this guy, it won't be tractable. Okay? You have analytical form, but kind of there is an integral which you cannot take analytically. But what is good is you can easily sample from this model, because you can sample from your Gaussian and forward it through your deep net, and you will get a sample. So this type of models are called implicit. So then, once you did this, you can also now you have a way of searching through this inf, right? Because now your model P is of this form, and theta are parameters. Okay, so here will be inf over parameters. Sup over, as I said, another deep net, which hopefully is flexible enough to approximate all the functions g. And here what you do is, this is a difference of expected values. Expected value you can estimate with a sample average, right? For that all you need to do is to be able to sample from the model. You have a sample from your Q, which will be the data distribution, and you certainly can sample from your model P, so get a sample here. Basically all this together means that you can't hope to perform stochastic gradient descent on this objective. Unfortunate thing is here you have min-max type of problem, meaning you are searching for saddle. Searching for saddle point is a nasty problem again, and this happens in extremely high dimensional space because, well, these deep nets which I introduced, they will have millions of parameters, and you are somehow hoping to solve this problem, which is something the person who is expert in optimization theory will tell you this should not be possible. Don't even try doing this. But nowadays people are very ambitious, and they tried actually doing that. So nowadays usually what people would do is, so you have two deep nets, right? One parameterizing your model, another this function g. You will start doing alternating steps. First you will make step with respect to parameters of p, you freeze it, then you make a couple perhaps of steps with respect to this g function, and so on and so on. There are no guarantees that you will find the saddle, but somehow people believe that, this is good enough. And indeed you observe that often what you get in practice looks good, and I showed you already pictures. Okay? Those pictures were exactly generated in this way. Once you stop training this procedure, you take this g theta function, you start feeding it with Gaussian noise, and it starts outputting faces, which you saw. And the thing is, if you specify f in a very particular way, you get the very original GAN formulation which appeared in the paper by Goodfellow. So,
Could you say difference of this approach with variational autoencoder?
Yes, so basically 2 days ago, or during the mini workshop which we had several days ago, I was talking exactly about that. And it's a bit orthogonal to this topic, so I'm happy to discuss this offline, but not right now. There is a difference. Variational autoencoder minimizes scale divergence.
Well, okay,
You can use it to minimize f-divergence, but variational autoencoder does it from the primal formulation, meaning it does not use the variational representation of f-divergence. It uses variational trick, but the other one, okay? Whereas this guy first goes to the dual and tries to attack problem from dual. So variational autoencoder ends with min-min. This guy ends with min-max. And because of that, the numerics of these two processes are very different, and you end up with different type of nasty problems.
But can't we always convert GAN to variational autoencoder using this min-min formulation?
People never use GANs with scale divergence f. That's the problem.
Never.
It appeared once in paper in this f-GAN paper, but they never do.
And if f is not log, you can't easily come to this min-min formulation.
Yes. You need to start with this guy, and what you do here. Min-min formulation variational autoencoder happens because for scale divergence you can nicely upper bound it in certain way where this encoder enters and you have inf. This variational lower bound is a usual term from Bayesian world. It does not hold for any type of f-divergences.
Yeah, but it is come just from Jensen inequality. The same is here.
True, I claim that you cannot repeat it for any f-divergence. Let's take it off. Okay, so now this is actually relevant. I described you everything I needed. Now you know what GAN is actually. Okay, what I wanted to say here is actually the way I explained what GAN is doing is actually quite sloppy. So actually there is a huge gap between theory I told you and what people are actually doing while implementing GANs, which means that perhaps what I told you is not exactly what is happening, but what I told you will be important in the next part of my talk, and this is so far, to my knowledge, the best way to explain what GANs are actually doing. So let's believe that GANs are minimizing f-divergences. So then I turn to the second part of my talk, which is actually not related to GANs at all, and I will just go through the results. So this is the problem. So assumptions. Let's assume that somehow we can solve these types of problems. So we fix f. Let's say we have distribution P, which we don't know, but we can sample from. For us, P will be the data distribution, let's say. And let's say we have certain way of finding good Q, which approximates this P in this f-divergence. So one way is, let's say, we can simply use GANs to do that. Okay, GANs will correspond to certain class of G, and they kind of work, so they do something. Let's assume that this is something we can do roughly, at least approximately. Then the problem is, now we want to do the same, but instead of Q, we want to use mixture models instead of Q. So we want to estimate P in f-divergence using this type of mixture models. Okay. And the thing is, let's say we want to do it in a greedy fashion, meaning we don't want to tune T capital coefficients and generative models simultaneously, because it's too expensive to keep them all in memory. Let's say we want to do the step-by-step iteratively, so meaning greedily. So we want at every step to freeze everything we trained before. We only want to adjust the new weight and new, so it's stated here. So first you just train your GAN or whatever model you have, and you end up with first model being just your first model and first coefficient being 1. At the next step, you choose certain coefficient beta and new component Q. You add beta Q to your previous model, but now you need to downweight all the previous weights by 1 minus beta, so that all the weights sum up to 1. Okay? This is our goal. The question is, how do you choose Q and beta? And that's a theoretical question, has nothing to do with GANs or whatsoever. We are just trying to approximate distribution of f-divergence. So, actually, I'm over time already or not?
Still not, but we have about well, half an hour.
Half an hour is a lot. I thought I have like 10 minutes more. Okay, cool, okay.
We'll make an exception for you.
Okay, so now that we know our problem, let me tell you the results, which are basically the core of our program, of our paper. And this was the reason it was not accepted to ICML, because they said, where are experiments? This is a paper on GAN. But we said, no, it's a paper on theory. Reject. So let's call this whole guy here, so everything we trained so far, let's denote it PG. Okay, this will be our notation. So Q is going to be the new component we want to choose, and beta is the weight of the new component we want to choose. Okay. So what we want to do is we want to choose beta and Q so that this guy is minimized. Okay, this is our problem. So this might be too ambitious goal, and instead we can also formulate a modest goal, which is, okay, let's at least try to choose beta and Q in such a way that this criterion in the updated model is at least smaller, strictly smaller than the criterion at the model we had on the previous step. Okay, so this just means that we just want to improve the current situation. And this C constant here models what is actually the improvement, how much are we improving. So this is a much more modest goal than saying we want to minimize it altogether. Okay? So the thing is, if we will try to minimize this guy, because we said that our models in most situations we can only sample from them, we don't have their analytical form. If we try to minimize this by sampling, so imagine the situation, we are training, we are making iterations, right? So the hope is we are getting better and better and better. So at a certain point, it means that this beta, in principle, should get smaller and smaller and smaller, because we want to make smaller and smaller updates to our model, because hopefully we are getting close to the truth, right? So, but then, it means that this beta should eventually, start going to 0, but this brings a problem, because we are trying to tune this by sampling, but at this step, we want to tune parameters of this Q, which enters this mixture with a very tiny coefficient, right? It means that most of the samples from our model will be actually from this part. And we will very rarely see samples coming from this Q guy. It means that all these mini batches will provide a very little signal on the gradient for the Q parameters. This is a problem. So what we propose instead is, instead of doing it in this fashion, what we will do is the following. So let's develop an upper bound on this expression. Okay. I will show you these upper bounds here. And these upper bounds are actually of a nice form. So these are two separate results. They have certain different type of assumptions, but basically they are both upper bounding this quantity which we actually want to minimize, right? And they are both of the following form. They come in two terms which are additive, right? So this Q, which we hope to tune, enters only this first term. Okay? So both results, first of all, they hold for any distributions R of your choice. Okay? These are just inequalities, so this guy can be upper bounded in this way for any distribution R. Well, there is certain assumption on R such that, this is still a properly defined distribution, but basically for any R. And again, this holds for any choice of R. These are two upper bounds. Now the trick is...
And is it PG minus beta R divided by 1 minus beta?
This should be, yes, this is a probability distribution, and basically this assumption says that it's a probability distribution.
Excuse me,
yes.
What is this probability distribution?
So if the densities of these two distributions are related in this fashion, so I define the distribution through its density here. You can see, if this holds, you can see that it's normalized to 1. So this is...
How can you multiply density by a constant? Then integral doesn't integrate to 1 anymore.
No, but this upper part integrates to 1 minus beta, and then I normalize.
Okay.
And this is non-negative, so this is a density. So here I'm defining distribution through density.
Density or the cumulative distribution function?
Density. Right. So now these two inequalities tell you how to upper bound this, and this holds for any choice of R. And cool thing is this Q, which we want to actually choose, enters only the first term.
Are they somehow related with the convexivity of these
Yes.
diversions?
Yes, yes, yes. So these are main results of the paper. So all 90% of the proofs are to prove these two facts. So
can you maybe like give like some example of like say if PD is a Gaussian, like how to get an R? Is it like possible? Is it easy or like it's like?
I didn't say what R is. I said this holds for any R, whatever R you want. You
But
choose.
say like if PD is a Gaussian, how can you low bound this like with R? So
Okay,
that you
there
know-
is beta, right? Beta is a coefficient of your choice which is smaller than 1.
So there are no experiments in the paper. It's
There are
just a
experiments.
result.
No, there are experiments. So, I mean, this has no contradiction. Here I'm saying because beta is smaller than 1, it's the weight of your next mixture coefficient. You certainly can find certain density which will upper bound beta times.
Yeah.
So now, the trick is because Q enters only the first term, what you can do is the following. Let's choose R so as to minimize the second term. Okay? So second term does not depend on Q, right? Only on R. Let's choose R, which minimizes the second terms, whatever upper bound you choose. I mean, these two upper bounds give you two parallel ways of doing this, but choose R to minimize the second term, and then choose Q to be close to this R. So this is not an optimal solution for minimizing this upper bound. But this at least has some intuition, right? So you're first minimizing the second term, and then you're trying to fit Q so as to minimize the first term. Okay? And this...
But we need to minimize with respect to R, which
Right.
satisfies those inequalities.
Yes, of course.
So
Yes.
it can be
Yeah.
not trivial problem.
I will show you analytical theorem showing exact form of
For
distribution.
any kind of F?
Yes, for any F.
Good.
One question. This requirement you have looks very similar to what you require in rejection sampling. Is there any sort of connection?
We didn't encounter any. That's maybe a nice question.
Because what I'm
But here
seeing
we
is
lower
that
bound, not upper bound. This is
Yeah, I'm
good.
not sure.
So it's a bit different.
Yeah.
okay, yeah, I see.
So now, so there are certain assumptions I'm putting in both. Basically, here is actually quite a strong assumption. This one, I'm saying that this f-divergence should be a Hilbertian metric, which is something weird. So this guy is a Hilbertian metric if square root of it is a metric. Okay? Hilbertian metric is such a guy, square root of which satisfies triangle inequality. It happens that Jensen-Shannon is a Hilbertian metric. And Jensen-Shannon is something most often used for GANs. Also, total variation is Hilbertian metric. Total variation is cool. It is a metric, but square root of total variation is still a metric. And the Hellinger has the same. So actually this class is quite large. So now, okay, so recipes, as I said, let's choose first R minimizing the second term and then try to fit our Q to R. Okay? So I will do it only for one of the upper bounds, for this one. Here is a theorem saying, so which R does minimize this expression? And it says, for any fixed beta, this is a density of a distribution minimizing this expression. So this is 1 minus 1 over beta, something, something. So this means if the quantity in the brackets is negative, you take 0. Otherwise, you leave it untouched. Okay? And lambda star is such a normalizing coefficient which ensures that this is a density. So this is non-negative by definition. Lambda star is such a guy which assures that this is properly normalized so that it's a density of distribution. And you can prove that such a...
Lambda star is not multiplying everything.
Yeah, only this guy.
It's inside.
Yeah, only this guy. And you can prove that such a lambda star exists, and it is unique. Okay. So this is a quite tricky form, but this minimizes this guy for R. Okay, you can prove it. Now you can do the...
What is the geometric sense?
I will turn to this.
Okay.
So basically, if you pull out dp outside, you see that it's a reweighted version of the PD distribution. It will be PD times something.
But with something subtracted.
Yes. But so
It's not
this is a non-negative. So some of the points will get cancelled because we will have multiplication by 0. But basically this will be, if you take PD out of these brackets, this will be exactly the weights I was talking about in the very beginning when I said I'm going to reweight my training set.
Okay. But I think that there should be more clear geometric interpretation.
Wait for one slide.
Draw some.
This is the other upper bound which I showed you. And here we again can try to optimize the second term. We end up with this expression. Again, lambda dagger is another constant which again, you know, normalizes this density. But now let me put them together. So these two bounds were developed independently, okay? They are based on different type of analysis. And we ended up with these two terms having optimal solutions which look very, very symmetric, you know? All we did is flip this lambda from here to here, and you get the solution minimizing the second upper bound. And we have no theoretical way of tie them together. We don't know why this happened, which is a bit weird.
And no dependence on F.
Another good thing which you notice is, look, these guys are meant to minimize, you know, this thing which depends on F. For some reason, optimal solution does not depend on F.
That's a bit strange.
That's a bit strange, I agree. So there are still many things to be discovered there, apparently. So what else did I want to say? Okay, so another thing we see is that this was our original problem. We want to choose Q, right, and beta. If you set beta to 1 and Q equals PD, you will immediately get 0. Right? So setting beta 1, meaning forget everything you did, choose Q to be the true data distribution, you get 0. In practice, this is something we don't want to do, right? As I said, we want to keep track of what we learned so far, right? So this means that from theoretical considerations, we failed to get an advice on how to choose this beta. So in our work, beta we set heuristically. Okay, so now that we minimize the second term, so I showed you how to minimize those second terms. So now we want our Q to match one of these optimal R's which I showed you, right? Okay. We found this R star minimizing second terms. We want to match them now with Q. So for now, assume we are infinitely powerful so that Q can perfectly match R star in f-divergence. Okay? This is an unreasonable situation in practice, but for theoretical purpose. So what we are going to do basically is take our current model and update it in such a way where Q equals either R star beta or R dagger beta, which I showed you before. Okay. So we may now ask, how are we doing in terms of our objective? Because our goal was to actually make this guy as small as possible. So the question is, how are we doing? And the thing is, we get geometric improvement. This is the criterion of the updated model, and it's upper bounded by -1 minus beta times criterion on the previous step. Okay. So by doing this upper bound business and doing weird trick, we ended up with some update which guarantees the geometric improvement. But of course, there was this unrealistic assumption that Q matches exactly this star guy. Okay. So this, I don't want to get into details, but we have a whole section on relaxing this assumption of matching it precisely. And this is a kind of a part of the paper which looks similar to the AdaBoost. In AdaBoost, every next guy should be at least better than random. Then we can weight them in such a way that overall it is very strong. We have a somehow similar result saying that if this is not 0, as I claimed in the previous slide, but at least smaller than some gamma times criterion we had on the previous step, and this should be actually F, then we again achieve the geometric improvement. Okay? So this shows that we actually don't need to match it exactly. We just need to be close enough to this R star guy, and we are still getting geometric improvement. So now, basically, this part is just to say that we are ending up with a very particular concrete algorithm, which is, so let's say we are using the upper bound corresponding to this R star beta. We had R star and R dagger. They are more or less the same. Let's take R star. It has this form, right? So take out this density outside the brackets, and you end up with certain quantity inside. In practice, the data distribution we don't know, but we will use empirical distribution. So 1 over n over the points of the training set, right? So basically, we have hard time because these weight coefficients entering this form, they kind of depend on this nasty ratio of the densities. PG over PD. But from the GAN literature, this is something I skipped. Basically, when you perform GAN and you remember the variational form of f-divergence, there was a sup over function g. If you solve this sup to optimum, then you can compute this ratio through the optimal discriminator z. This is another sloppy step, but well, this is an algorithmic part of the paper and we need to do some relaxations. Basically, it tells you that this ratio can be computed through this optimal discriminator, and this is exactly training classifier to tell the fake examples generated by your model from the real example and reweighting everything. And then you end up with this guy being the reweighted training distribution, where the weights depend on these things. And here, just to tell you what happens. So D is a classifier which tries to say 1 for the true images and 0 for the fake images, okay? So if D is very close to 1, it means that perhaps our current model is not covering this part. And we will end up with quite a large weight, because this will cancel and we will just have this. If D is close to 0, meaning it's, makes a confident prediction that this is a fake example, these things blow up and this zeros. So this is a very aggressive strategy of reweighting. We will actually zero out some part of the training set. Okay. And finally, to turn to a couple of experiments which are very sloppy, but...
And could you explain what is lambda star? Like
yes.
How do you get that?
How do you get lambda star? It's 4 lines. Basically, lambda star is defined from the fixed point equation. You want this guy to sum up to 1. This is a discrete measure on endpoints. You want to find such a lambda which sums up to 1. You can do it linearly, basically, in number of points. It's a quick update step. Okay? And then you use these weights as the important sampling weights for the GAN on the next stage. And some of them are 0, meaning some part of the training set your next GAN is not even going to see.
Yeah, but can they come back further?
Yes, they can come back further. Especially if coefficients of the previous models get smaller and smaller, then you will rarely observe dogs, let's say, and you want again to cover dogs. And we did several experiments. So first ones were just with we are generating mixture of Gaussians in here 2-dimensional space. We are generating mixtures of Gaussians, and we are trying to cover them with GANs. And the single GAN has hard time covering all of them. But basically, so what we measure is, we call it the coverage. So this is our model. We are measuring part of the training set covered by our model, where this T is a threshold, is basically a quantile of the model distribution. So what we are doing is, there is a model distribution, we are taking a 95% quantile of it, and we are looking at how much of the original data is covered by this quantile. Okay.
And does this quantity somehow include the quality of samples? If you model samples from the wrong
We are not, no.
It's not there.
Okay, this does not model it, yes. This metric ignores the quality of the samples. I mean, on the other hand, here, Gaussian, what is the quality of a point in 2D space? It should be close to one of the Gaussians.
Yeah, likelihood.
If many points are far away from our Gaussians, then this guy will be small, because these points will affect the quantile, and the quantile will go away from the real Gaussians, not covering them. So somehow it is still included. And basically, the takeaway message is this AdaGAN improves a single GAN. It improves best of T capital GANs. So imagine running T capital independent GANs and taking best of them. So of course it improves, but it also improves T capital independently trained GANs.
Like if you randomly choose among them and then sample.
Exactly. So what you can do is you can train T capital independent GANs and then uniformly randomly sample from them, and this is your generative model.
But again, you're not explicitly saying that these T randomly trained GANs should correspond to different modes.
Yes, no. You just train T capital independent GANs on the same data set. You run it in parallel.
So that's not surprising. You should be better.
Of course, yes. Sure. So this is just a benchmark to say that we are doing as expected better than that. The thing is, so this is just to say that so we use more modes. So instead of 5 Gaussians, we use 10 Gaussians, and actually with more Gaussians, we are the improvement over those two baselines is actually increasing. We are doing even better. But also we compared to one of the versions of GANs which tried to address specifically the missing mode problem was called unrolled GANs. And for some time they were hyping, people were citing them a lot. The thing is, if we use AdaGAN and use unrolled GAN as a black box in every step of, so if in our AdaGAN at every step we are doing unrolled GAN, we are still improving it. So we are doing better than unrolled GAN, but we are actually even improving it. And basically the message of the whole talk is AdaGAN is not some algorithm which we claim to be better than others, but it's a framework which you hopefully can use to further improve your own implementation of GAN.
What about T-independent unrolled GANs?
What about what?
T-independent unrolled GANs. Are they better than AdaGAN or not?
That's a nice question. I don't have picture here.
Because
Actually,
these two models have approximately the same number of parameters. So it's fair to compare
so
between them.
the thing is, unrolled GAN with 5 steps is more or less, we computed the time, is more or less the same computational complexity as 3 steps of AdaGAN.
For training,
For training.
not for some.
For training.
You mean computational complexity in terms of time?
Yes. So, because 5 unrolling steps is actually you're making 5 times more gradient updates and then you roll back. And AdaGAN, it takes 3 steps of AdaGAN to reach the same time.
And what about unrolling one step and then computing the bagging of a lot of...
Yeah, this is something we didn't do. We didn't do bagging, so this independently training and uniformly weighting, we call it bagging, of course. We didn't do, I think, bagging of unrolled GANs.
Oh, what is the unrolled GAN idea?
Can we do it offline, please? Okay, but the idea is you have this alternating game between generator and the discriminator and minimax. Unrolled GAN is basically, so correct me if I'm wrong, I think you're making several steps further with discriminator. Instead of doing 1-step discriminator and then generator, you do 5 steps of discriminator, you update generator, and then you roll back.
I think you actually unroll like several steps of the game of both updates.
Yeah.
And then you backdrop through everything.
Yeah.
So basically you have like a meta...
Basically your generator looks into the future. It's not just taking a decision based on the current discriminator, but actually chooses where to go.
Okay.
And then finally, just to say, we ran experiments both on MNIST and CFAR. Conclusion was there are no existing metrics which would allow us to compare our model in any reasonable way to the others.
Have you tried C2ST of the...
C2ST was not there yet when we published this paper. We tried all the rest. We tried many other
Well,
things.
it was an archive like last year, October.
This was, we've submitted this 1 week after Barcelona conference.
So it was December.
Yes, there was like...
2 sample test was October, you see?
No, well, okay, but...
You need to check. Okay, mate. This we didn't try. Basically, so this is just to illustrate. So what is happening here, this is the last slide, so don't worry, I'm done. So, so we did 1 step of GAN with MNIST, okay? The bottom row are the true MNIST images, okay? And these are the most down-weighted images after the weight update, meaning our current model seems to be missing those. And these are the nicely covered. Do you see any difference between these two?
Yeah, October 2016.
Okay, you killed me now. Reviewers were not aware of.
We should
How
compare
many
many
parts from
sevens.
the video?
Yeah, but so to me it looked like these are thin and these are not that thin. Okay, the visual evaluation starts, right?
Yeah,
But-
we are starting comparing blurriness of like...
But basically, this is what our first model was generating, which indeed looks, thicker than those. And after the update, the next started generating this, and at least I see more thin ones here. But again, of course, this is totally subjective. And yeah, to conclude, I think in the course of the talk we already mentioned most of the pros and cons. One con which was mentioned by Anton is now instead of having one GAN, one function mapping, we have T capital of them. And there is no way now to talk about the manifold. One GAN we could invert back and to get latent vectors for a given image. Now we cannot do that because we have T capital of them. And this is one of the further directions. Right. So increased complexity as noted already. So otherwise, everything was already pronounced. So if you have any questions now or after the talk, and I'm done. And those of you attending NIPS this year, come see our poster.
Wait, but your model is a mixture of many GANs. Can't you just mix their manifolds and just make discrete choices?
Yeah, we
of the
can
manifold?
invert every out of T capital ones, but it takes inverting GAN is a fairly hard procedure.
But the problem will be, the problem is that like,
You
when
just
we
need
talk
to
about
do-
manifold, like we want to interpolate,
Yeah.
say start at one image and go to another.
And we will
then
have
this
holes
GAN-
between.
Well, yeah, you don't switch from one manifold to another exactly because you will pass the zero probability area. You just stay on the same manifold and
Basically,
inspect them independently.
You will be on the manifold, and then suddenly from here you will jump here in a discontinuous manner.
No, I
which
think
is-
so, like what will end up, you will end, if you try to interpolate this, you will end up averaging in the image space, which is kind of like a nasty thing to do, like interpolating directly in pixel space.
Yeah, actually
It's
what
like,
you want to do is you want to take an image and return a latent code. So how do you do that? By having T capital GANs. You will invert it with respect to every GAN, and then you will have to interpolate these codes,
Yeah.
or it's not a...
I don't know, I guess you just need to first classify the image, determine which
Let's
of
do
the
this
GANs.
for next paper. And we will
No,
submit it
actually,
to the next
regarding the next paper, I have a better idea. I mean, come on, we already have. You just presented us the AdaGAN, the AdaBoost for GANs. Okay, we know that AdaGAN, AdaBoost is meh. There is gradient boosting. So when will we have the gradient GAN?
Sure, I'm happy to see this paper soon.
What about adversarial autoencoders? They don't have node collapsing.
Very nice question. I mentioned this in the talk at the mini workshop. I'll be happy to discuss with you. It's a bit again orthogonal topic. Basically, adversarial autoencoders, I can prove that they are not optimizing f-divergence or KL divergence. They are optimizing two Wasserstein distance. It's a totally different beast, and they have different properties because of that from VAEs, for instance. So yeah, they were introduced as a way to improve VAE, but actually they ended up with algorithm doing totally different thing, which is minimizing two Wasserstein distance instead of KL divergence as they were hoping.
But also like to comment on that kind of stuff. I think like for the moment, like at least all the papers I know which are going back and forth with like GAN representation, they lose image quality.
Yeah.
So that's why like they just samples are worse.
Yeah, but you can also add a discriminator on the output of the decoder of the adversarial autoencoder.
People try to do that, but like in the end of the day, they lose quality. So like I haven't seen any paper that can go back and forth without losing quality.
There is a paper called Adversarially Learned Inference, which achieves quite nice samples, but they have a hard time reconstructing even training images from their latent code, so it's all...
So like I think like for the moment, like doing both, like doing reconstruction well and actually like having like DC GAN quality images,
It's hard.
that's open problem.
Yeah.
So it's
So
like,
no silver bullet. It's actually a growing field, so there are many questions to solve. Jump in. But start with developing a way to compare different GAN models, because this is something missing. People are comparing like I did with this slide. You clearly see the thin, right? unless you convince the reviewer, you know, he will say, yeah. Some of the reviewers, they're like, oh yeah, I see the thin. The others, they're like, no, I see more sevens here and...
Actually, like another comment as a practitioner of these things, it's very important to have the same software that saves image to a
Exactly,
file. Because
exactly.
if you use slightly different interpolation,
Python's default first smoothes the image.
yes.
If you generate a picture and then save it with Python default, which function is that? It smoothes it. And you will see very smooth image, and you will be like, oh, I'm creating something good. But if you turn off the default, you will see a huge pixelized image. No, this is, I think even in some of the published papers this happened actually. I mean, it's not a hack, because you can still use Python to smooth it. So in the end, you're creating smooth images.
Yeah, but like the problem is like for one method you do this, and for another one you don't. That is the issue.
So,
Yes.
like if you want to optimize the optimal transfer distance, what do we do?
It's a whole different things. You can do it with the same approach with the discriminator, which in this case is called critic, but basically it's a different topic.
No, we
But
don't
like,
have this qualities, right?
Did I understand correctly that AdaGAN is not directly applicable to that because you won't have divergence?
So yeah, the thing is, AdaGAN starts with saying, let's say we can do this, right? And because of that we were using GAN. But so this is a sloppy part of justification. You could do the same with WGANs, which are not minimizing f-divergence, but Wasserstein distance. The hope is, if you're able to minimize Wasserstein distance good enough, perhaps it will also have a small f-divergence in there. So I mean, there are many sloppy parts in applying this theory to the GAN, right? So why not adding one more sloppy part and doing WGAN? So AdaWGAN, or basically the claim is this is a framework. Use it, try using it with whatever black box implementation of unsupervised generative model you have. Try to do it with VAs. I mean, should not be a problem. I mean, it's something you can do in experiments, so why not trying it out?
Okay, any more questions? Then let's finally thank the speaker.
Thank you. Okay, that's it.